You're live, Andrew. You can start.
Okay, hello. Sorry, I wasn't sure I was live there. Right, my name's Andrew Dinn. I'm an engineer in Red Hat's JDK team, and I'm a member of the OpenJDK project. I've been working on OpenJDK for over a decade now. I'm also a contributor to the GraalVM project, actually been doing that for over 3 years. And what I'm going to talk about today is how native images, particularly Graal and VM native image, fits into the roadmap for the for where Java's going from the point of view of the OpenJDK project, and what we need to do in OpenJDK to respond to it and to try and make sure that things go smoothly. Being in both projects, that's obviously interesting to me, but I think it's important to everybody that the traditional Java and native image both move on together. Sorry, just a second, I'll move on. Okay, so this is the basic subject of the talk. Where does native image fit into Java's future, and how does it relate to traditional Java? I'm going to talk about what a native image is. It's clearly a different deployment model to the standard way of deploying Java, but there's a bit more to it than that. I'll talk about GraalVM native image. The real question is, it's clearly the preferred way of deploying images for containers. Is it a definitive version of what Java should do when you use this deployment model? Or does it need standardizing in some way? The reason is we don't need a gap to open up between what is expected of the dynamic VM and what will happen in a native image. And then I'll talk a bit at the end about Project Leiden, which is a sub-project of OpenJDK. And the thing that we're interested in from Leiden is making sure that whether you deploy as native or as a standard deployment, that Java's right one once run anywhere guarantee is maintained. So let's talk about what a native image is. Obviously, it's a different way of deploying Java. You take all the classes that are in an application jar, all the library jars, the JDK runtime classes, put them through a native image generator. It's all compiled into one single deliverable. No need to upload a JDK, no need to deploy jars or pull them off the internet. You just ship your binary like you would with other languages. It's much more container friendly, and there's some reasons for that. One of the things you can do when you're building a native image is actually only build into it the code and the data that's needed for the application. Now, when you run the JVM itself has state. The JVM has to initialize itself. It's got things in there like an interpreter and a compiler so that it can cope with the code base evolving over time and execute things as they arrive. A lot of that can be ironed out up front and removed from the target. So this gives you both a smaller image, and because you're doing less preparation for what might get thrown at you in the dynamic runtime, the conventional Java, you also can start up faster, and you can actually pre-compute some of the state you need as well. So it's definitely friendly as far as containers are concerned. And particularly so for microservice applications where you've got relatively small processes, because in monolithic applications where you've got traditional Java and the whole Java is running, say, in an app server with lots of sub-services and so on, the actual amount of space and the amount of startup time taken by the runtime is relatively small compared to the application. When you've got a lot of little small processes, that can be a significant amount of your total deployment size and your total startup time. So it really matters to use this model for containers. But what you have with a native image is most definitely a reduced Java. And it's not so much that you can't get mostly the same functionality. GraalVM is almost complete in terms of what you can deploy, modular a few things. But there's various choices that in the standard traditional way of deploying, you would be able to make at runtime and revise at runtime. You could decide what to run on the basis of what happens previously. You can't really make those decisions at runtime with a native image. A lot of the decisions you make about how the code's going to operate and how the application is going to run have to be pre-decided at build time and pre-configured at build time. And that's both to make it possible to compile it ahead of time, but also to get some of the performance gains that you need to get footprint and startup down. So let's look at what sort of things I'm talking about here. What are the elements of dynamic Java that are not necessarily exactly reproducible in a native image? Well, the code base evolves during execution on the JVM. Classes are loaded as you go along, but the actual set of classes you might load can be arbitrarily extended at runtime. You could pick a URL and load something off the internet. The service provider interfaces that are used to identify how to plug in various servers like file system providers or middleware provider services for middleware components and so on. These are things that are decided at runtime, often actually on the basis of a resource file that's in a jar that provides the service, but you could actually compute which classes to load for wholesale components of your application, and you could implement them differently with a dynamic choice. That's really got to be decided in advance in a ahead of time native image. Classes can be created on the fly in a standard VM. You can either create proxies or wraparound behaviors, or you can even create classes to do custom operations. So it's a very different picture to the one where you have to make these decisions up front. And the language reflects that dynamic nature. There are mechanisms of the language for investigating the state of loaded classes and accessing data, creating instances, running methods indirectly, reflection in older versions of the JDK being supplanted by the use of method and var handles. So the language is built to reflect this dynamic evolving code base. The VM options and tools are all configurable when you run the program. You can decide which garbage collector you run, whether you run interpreted or with one JIT or two JITs or an external JIT like the GraalVM compiler. You can decide whether OOPs are stored as 32-bit offsets or 64-bit pointers. You can decide which of the hardware, math, or crypto capabilities you want to rely on. And then the tooling is also built around a dynamic model. You can load agents at any time during execution, and they can modify the code based on the fly. The debugger model relies on de-optimizing compiled code so that you can actually execute it via the interpreter in step and even redefine classes. The flight recorder tool that's used for monitoring that generates events for the JDK runtime and the VM will also allow events to be defined by application classes, happily create them and pop them into the event stream. It responds to the changes in loading things in the code base. And there are ways of talking to the JVM and the JDK runtime, things like JMX and JCommand, that allow you to investigate the state of the runtime and interact with it and update it. So these are all things that actually are things that can be done as late as possible in the conventional Java. And these things really need to be identified ahead of time if you're going to use the same capabilities in a native image and compiled in. So it's not just the closed world assumption where just people talk about where all the code has to be identified. There's actually all these other things that need to be decided in advance. And that means you've got the option to pre-configure pardon me, and pre-initialize things as the flip side to this, where the JDK runtime on the JVM has to do all sorts of things at runtime. Those things are decided in advance. There's optimization opportunities for you to configure and even construct some of the application and runtime state in advance when you're using a native deployment. So it has benefits as well as losing some of the flexibility. So does that mean static Java is really dynamic Java? They're the same thing? Well, I like, definitely, with some of the choices made early. How like is like? Does this really mean that you've got different semantics for your Java application? Or really just talking about having a different execution environment, a different execution profile for the same code? It's a bit of a moot point, and it's not really a simple answer. I mean, that Java environment that you're changing is Java code. So you are changing the semantics of some of the JDK runtime, but not in any really significant way. You can get much the same behaviors if you configure the right choices for any of the things that an application might do. It's just you've got to pre-commit to them. But there are some choices, and particularly things around optimization, that may affect language semantics. And this is particularly to do with build time initialization, which I'll be talking more about later. And that means that when you prepare and pre-configure an application, if you were to run the code that you pulled in from the JDK runtime or from your application or middleware as is, having pre-initialized it at build time, you wouldn't necessarily get to work exactly the right way. So there's a need to correct some of the things that are actually different in the runtime that were set at build time. And GraalVM provides a mechanism to do that. And making sure that's done in a standard way, both in the JDK, for middleware and for application, is one of the things we really need to formalize and put some hard and fast rules down. We don't think there's a problem with how GraalVM is doing, but we want to make sure it's done right and it continues to be done right. And that Quarkus and other tools in middleware do the same thing and do it all the same way. So let's move on to GraalVM Native itself. Yes, it's definitely still Java. And GraalVM Native actually provides a fairly complete implementation of Java. It's caught up with Java 11. It's actually keeping track of Java 17. So really it provides the ability to run pretty much most Java applications as native images that you would normally run the dynamic JVM, and essentially run them in the same way. GraalVM actually asks for help for you to close the world. So you need to configure various things that are ambiguous, like if your reflection target's not clear, you need to bound the scope of reflector operations. You need to say which services you want to load, although Graal will try and find the ones that you need and load the things that you need. So there's various things that you have to configure in advance to get it to work. The actual VM options need to be defined in advance. These are only enterprise options. The garbage collection and collect compressed oops are available in enterprise at Graal. You have to pre-commit to that because when you compile the code in advance, you need to put garbage collector barriers into the code. And so you need to decide how that's going to be written. Doing it dynamically would involve a lot of call outs. It would be really inefficient. Similarly, if you want to use 32-bit pointers rather than 64-bit pointers, that changes your object size. So you really need to commit to that in advance. And similarly for some of the other things that configurations that are normally done at runtime. On the tooling side, we've been working with Oracle for the last year, putting in support for debug info in the community edition. There was an enterprise edition debug capability. I've implemented that for community edition, so you can use GDB or Visual Studio that my colleagues worked on to debug applications. We've also just got a PR now just raised to get Java Flight Recorder support in, which our team have been doing with the help of a couple of people in Oracle. So we're hoping that by September, we'll have a fully working flight recorder capability, which you can build in and enable or disable when you run the program. So you can see both runtime events and also application events. There's nothing equivalent to JMX or JCommand at the moment. If we do get something like that, it's probably going to look somewhat different. So the story's not completely there for all the tooling, but it's getting there. So Graal is pretty much a complete Java and is up to date and gives you most of the things you need. Now, so is that a yes? Well, the one area, as I mentioned, we've got to still think about a bit more and do some more work on is build time initialization. Now, this arises because in a normal JDK runtime deployment, when you load a class, that's a clear point at which you initialize the class's state, its static fields. You run a static initializer. And in a pre-built Java that's a native image that's been pre-built, the class is already loaded. There isn't any point to actually load classes. So when do you run the static initializers? You could find an equivalent point during execution where the class would have been loaded if it had been running the dynamic VM, and decide to try those points as places where you might try and static init the class. And the first one you reach, you do it there. Alternatively, you could do static init just when the program starts, initialize all the classes at once, which would be a bit more efficient. But it's even more efficient if you can build time initialize the classes when you're actually preparing the image. Now, it's usually safe to do that because most static inits just set default values for class fields, for static fields, including constant final fields. And that's really all they do, a lot of them. And that's true for a lot of JDK runtime. And that's a really attractive thing to do early because a compiler can actually take the final fields and treat them as constants when it's building the native image code. This is something that you get automatically on the dynamic VM. You never actually compile methods until a class has been static initialized. So static fields are always constants. You can fold them into the compilation. Now, there's a lot of compilation optimizations that are available, what's called constant propagation dead code elimination. So as well as throwing away the initialization code that you don't need to run anymore because you've initialized static state, you can also throw away code, say in an if branch, if it tests that a value is greater than 0 and the field has value 0, you can just compile the else branch. Or if there's no else branch, you can throw away that code. So this optimization allows you to squeeze a whole lot of extra code and classes out of the closure for the program. And it's really important to use it. The problem is that moving initialization to build time or even changing the timing of it can actually alter the way things initialize and sometimes cause initializing to happen differently in a way that wouldn't happen with dynamic VM. It's very important that if one class depends on another class and its state is computed from that class's static state, well, then you keep the order. But actually, the timing even can matter for some things. There's also a whole lot of cases that GraalVM looks at and it rejects static initialization for certain commutations. There's no point initializing a static field that has a time in it at build time because it'll be out of date at runtime. A field that is computed from host, operating system, process, or hardware specific data is not necessarily going to have the right value when you run it on a runtime host that's different. Crypto keys, random values, you really want to compute them at runtime. You don't want to have the same random value generated every time you run a program. And values that are computed by calling unsafe or calling it native code, you don't know where they've come from and how they're computed. It's not safe to initialize those, and Graal will reject classes which have initializations like that. It also won't allow you to initialize a class that creates a thread, which you can legitimately do in a static init. There's no point having a thread in the build time environment. It's meant to be run in the runtime environment. Now, by default, Graal doesn't build time initialize JDK code, but it will. And we're fine with that. We think it does it all correctly. We haven't got any places where we think there's anything going wrong. Obviously, that needs to be kept in sync with the JDK. If the JDK code changes, the init code needs to be checked to make sure we can still safely static init those classes. But that's just a requirement for us to cooperate with the GraalVM team to make sure it's okay. But GraalVM recommends using built-in init sparingly, and there's reasons for that. I'll just come to in a minute. The client frameworks tend to enable it as much as possible. The reason for that is if you didn't initialize JDK code, every class you rule out will rule out all the classes that depend on it for their initialization. And so you can have a cascading effect where a whole load of classes can't be built-time initialized. So not initializing JDK code, or even just a few classes, can cause you to lose a lot of optimization opportunities. But the problem is that some of the initialization that really needs to be done to make the runtime capable of running in the JDK, or some of the middleware initialization that you want to do to have other things optimized, isn't going to do the right thing. It's going to build in things that depend on the build time state, which will be invalid. And I'll talk through an example of that to show you what I mean and show what Graal does to fix this. Basically, there needs to be a repair mechanism. Graal provides this for JDK code. The same Graal mechanism is used by Quarkus and other middleware tools to repair things in middleware libraries, enterprise libraries, and applications sometimes may need to do this because the need to initialize some things to be ready to run means that actually you've got to reinitialize and correct some things that were wrongly initialized. So here's an example from Graal. We've got a file system provider API, which is a plugin point for accessing different file systems. There's always going to be a file system provider for the local file system. So if you deploy on Linux or Mac OS, it'll be a Unix file system provider. And there'll be a Unix file system for the local host file system, which will be an object stored as the value of a static field, and other things that need to use the file system will need to refer to that file system instance and that provider. So they need to be initialized up front. But the fields that are in that object, the default directory and root directory, are created at build time when the Unix file system is actually the build time file system. So those are the wrong values for the runtime system. So we've got to build this object into our image and have it pre-initialized, but it hasn't got the right data in. That means we need to reinitialize it. Now, luckily, Graal, because it's got to build everything to run over an alternative VM, has a mechanism for doing global substitutions of classes. Build time classes can be replaced with alternative classes that have different behaviors. So we can generate, instead of Unix file system, we can actually compile the image with a class, a target file system that has repair behavior that will correct the actual data that's in this Unix file system to use the runtime data or reinitialize it. And this is done globally so that anything in the code base that refers to a Unix file system in the original source code will be compiled to use a target Unix file system. So what's the repair? Well, there are three fields in the object that need to be updated. The provider field is actually kept as is, although it's actually an instance of a class that's also transformed and replaced. But it's still there, and it's still whatever object we started with, modulo the substitution. But there are two fields that we want to make sure get updated. This field default directly and the field root directory, which are referring to the build time file system. So these fields are virtualized. The file system actually has these fields deleted when it's written into the image. And anything that tried, any code that tried to access this field that did a get field on default directory or a set field on default directory would end up calling a getter or a setter method that's provided on a class that Graal provides called Unix file system accessors. So we're indirecting the original code. So these fields are no longer used, and they reuse some different data. And the substitution class actually has some different fields injected into it instead. So it's got the provider, but it's got a different injected default directory and root directory field. And these are used as targets for the getter and the setter. They've got the same types, but the values of these are recomputed the first time a get happens. Now we need to know whether that's happened or not. So we have a volatile field, because this might happen with a race. And this volatile field initially has a value that says needs reinitialization. And when the fields have been recomputed, it says initialized. So we can tell at a get whether someone's already done the recompute, run the recompute, and then if it's already been done, just return the value from the injected field that we want. So this is how we control the reinit. Now, in order to initialize the class, we could just go and write all over those fields, but they're actually computed using some logic that's defined in the constructor for Unix file system. So what this code does here is this hijacks the init method of the original class, and it binds it to a newly introduced method. It's a native method. It doesn't have a definition because its bytecodes are going to be hijacked from the original class. And when we call the original constructor, it will run the original constructor, except it's been modified by the rewrite. So it takes a target Unix file system provider and then the user directory string, which were the arguments you'd have in the original module of the substitution. Also, when it writes the default directory and the root directory, it's actually going to call the getters, which will update the injected state. So let's look at the actual setters and getters here. The setters for the two injected fields, they both just write into the substitute field that we were using as an alternative storage. So they get given the file system and the value to be written, and they just assign it. The getter has the logic to do the reinitialize. So something tries to get a default directory from a Unix file system. In other words, if the code originally had a get field on field default directory, it's going to return injected default directory. But as a one-off, if the state hasn't been changed to reinitialize, we'll call a method that will recompute the data in the runtime. What does reinitialize look like? Well, it's a synchronized method because there's a race on here potentially. It does double check locking. If we still haven't yet run the initialization, we got there first. We call original constructor, passing the current provider and the user data property, and that will recompute those two fields correctly, and we'll rewrite them, but end up rewriting them into the injected fields. And then after we set that flag, we're now reinitialized and everything's back to normal. We've repaired things. Now, that's interesting. There's a way of dealing with the fact that built-time initialization can sometimes do things that we don't want and repairing it. It would be better in many ways if we could have things in the JDK runtime and in the Java language that would allow this sort of reinitialization to be done without having to go through all this complicated processing. There's a danger that this could go wrong if the JDK code changes. And there's also a danger that if it's done in middleware, in different middleware implementations, it could be done in slightly different ways and we get different behaviors. So we really want to standardize this, and we want to make sure we know what's actually going to be possible to vary here. So this is what Project Leiden has been proposed in order to do. The most important goal for Project Leiden is to extend the existing Java standard for the Java SE standard, which is all about the dynamic VM, so that it actually also allows for static deployments, for deployments where things are pre-configured. And obviously we need to identify what things may or may not be pre-configured, and also what must or must not be pre-configured, where the hard rules are. So we need to really identify what behavior is allowed to vary and how it's allowed to vary. And if possible, the design of the development of the JDK runtime should make sure that we respect that and make it as easy as possible to ensure that the static case is dealt with along with the dynamic case. So it would be really good to integrate these two things and not rely upon having to have some complex mechanism like there is in Graal, or at least make it more simple and more straightforward to Graal to achieve the results it wants. Beyond that, we also need to extend the TCK conformance test suite that's used to say that something is a valid Java implementation, so that it recognizes both dynamic Java and static Java, and we can test that static Java implementations are conformant. That means we need not just to test a whole load of test programs by generating images and making sure they do the right thing. We'd also want to make sure that the behavior of the generator program is conform. There are standard options, standard ways of driving it, and different outcomes if you choose different options for how to generate the images. The proposal at the moment is also to implement a native image generator as part of Hotspot, using Hotspot components to do that. And then we can have an independent verification of the test suite using the reference implementation for the generator. And we can be sure that the TCK is passed as far as Hotspot is concerned, and then we can hand that test suite over to GraalVM or any other implementations to see whether they also are conformant. So the point here, the real end goal of all this is that Java's always prided itself on being write once, run anywhere. The same code will run in all deployments the same way. And we want that to be true for static Java as well as dynamic Java. And we want it to be very clear from the specification that when you are executing your application on the dynamic JVM, you know that a whole lot of things are going to be exactly the same if you use the native deployment, and there are only certain areas where things might vary. And similarly, if you develop something as a native image and you want to run it in dynamic Java, vice versa, the two things will remain the same, because we really want that continuity. That means you know where you're going to go and the two things are not going to diverge. Right, so that's the end of my talk. Thank you very much for listening, and I'll be happy to take any questions that anybody has now. I think we've got a few minutes left still. Right, so first question. When we go to native, we lose the JVM ability to optimize and de-optimize the compiled code on the fly. Is it worth it just for faster startup times? Well, this is an interesting question. I think if you were to run an application for many hours or days on the dynamic VM, the de-optimization and re-optimization that happens as the application develops means that you gradually tune the JVM. And in many cases, not all cases, you gradually reach peak performance where code is optimized and re-optimized and re-optimized. And the stuff that's running all the time gets as fast as possible. Now, if you're compiling code ahead of time, you can't necessarily identify in advance all of the optimization possibilities, and you can't actually tune the code as much as you can when you're re-optimizing on the basis of continuous feedback from long running. So there's a sort of sweet spot where if you run for a certain amount of time, you start to get benefits from the recompilation, even though you're doing all the work of compiling and recompiling. That compile overhead at startup actually slows down startup quite a bit, because you're compiling a lot of code, including a lot of static code, static init code that's compiled once and thrown away. So it's only really for longer running applications that it matters. And if it really, really matters you start up fast, then that compilation overhead is really going to get in the way of you getting your application up there and responding quickly. But if you really want peak performance, you'll probably get better peak performance out of the dynamic VM. So there's really different choices here. And it's not like you just have to use native image. It's sometimes worth paying a bit more overhead in the VM and a bit more overhead for the time for compiling to get better peak performance and peak throughput. Maybe as Graal improves, maybe as the compiler improves, some of that will be clawed back. There are techniques to do that, but I think there's limits to how much you can claw back. So, of course, with a lot of microservice applications, and certainly with things like function as a service, serverless code, you just want to do a quick run and then close the thing down again. So you wouldn't really run for long enough to get any benefit out of compilation. So, you know, it really depends. These are different deployment models for different purposes with different trade-offs. It's not an absolute thing. What's the time schedule for Leiden? That's a good question. Well, Leiden took quite a while to get started, I think mainly because of trying to sort out what's going on between the OpenJDK project and what's happening in GraalVM and getting GraalVM stable with JDK 11 and 17. So we're trying to, Red Hat, we're trying to actually start making progress on building a reference implementation, investigating still very experimental work. We think that we may be a couple of years before we actually have a full reference implementation. Some of the specification work could still happen quicker than that, and a TCK, or at least a TCK suite for static Java, and maybe even some exemptions for the current TCK for cases where it doesn't make sense to run some of the tests in a native deployment, the static deployment, because they're really only appropriate for a dynamic deployment, that could maybe happen a bit quicker. So we might start to get to a point where we've got a standard and a conformance test mechanism for Graal even before we actually get a reference implementation. But I would think it's a matter of a few years. It could be longer than that. It really depends what sort of job we do for implementing Leiden, how much work we put into it, how much we try and make it a really full quality implementation versus just a simple basic reference implementation. Do application developers have to be aware of all or most of the native image properties and configuration, or should this be offloaded to underlying frameworks usually? Well, the stuff that's to do with the middleware code hopefully would be dealt with by configuration that's provided by the middleware tooling, because application developers can't really be expected to understand the nitty-gritty details of all that tooling. But it would be nice if it was exposed with a mechanism where clear choices could be made by developers so that they could configure the middleware to get things that they would want. And that's what Quarkus has put a lot of effort into working on. I know it's been one of the usability has been a very important part of the way Quarkus has developed. I'm sure other middleware offerings that rely on native image are doing similar things. But yes, there is a need for a lot of that work to be done by people who really understand what the middleware is doing. And similarly, one of the reasons we want to align GraalVM more closely with OpenJDK is these decisions are being made about how things work in the GraalVM project. They have a very good understanding of OpenJDK, but they don't know what we're changing in the OpenJDK project. And so we really need to get together and be communicating and making sure that things are done consistently. So yes, as far as the application side is concerned, I would hope that the application programmers would be able to concentrate mostly on the application itself and ways of making the application work the same in either dynamic or static deployments. Next question. Is native app run faster than a regular Java app? It depends, but as I said, a lot of the compiler options that are available in a regular Java runtime are not necessarily available in a native runtime where you're compiling ahead of time. One obvious example, Hotspot only compiles the paths that have actually been executed, and it throws away code on paths that have never been taken. Now, sometimes it has to recompile a method, but that means you actually compile a subset of the code, the stuff that's hot. And if you're only compiling some of the code, that means that the cases you have to deal with are less, there's less combinatoric possibilities. So certain optimization opportunities happen that wouldn't happen if you compiled the full code base. You also know which is the hot path, so you can put all the code that has been traversed in line, and you put branches that aren't normally taken but might be taken out of line, so you tend to get better code cache locality. If you don't know which things have been taken more often than others, which you don't know ahead of time, you can't do that stacking of the odds of staying in the code cache. So there are various sort of compiler techniques that you could try and win back, and there's things like profile guided optimization that would do that in GraalVM, but really they're limited by just not having the profile information that you gather during execution before you JIT compile. Of course, the other side of the coin is you spend some time compiling, so sometimes things might just be faster because they just run and they don't spend time compiling to get to peak performance before they run. So if you run for a short enough time, yeah, you'll probably be faster with a native image. It's really not easy to give a straight answer, but for long running things, I think the dynamic JVM is probably going to win, but not always. You know, I mean, it also depends on the actual code. Are there any plans to support JMX in the future? I don't know, but I would think it's unlikely because this JMX is not a protocol that a lot of tooling that's used in containers is going to be happy with. It's more likely that things that would want to be exported out of the JDK runtime would be exported using some other tooling. And now, while that might need things to be added to the dynamic JDK to make that possible, those might be things that might be just built into Graal straight away without building in anything equivalent to JMX. So obviously we built JFR in because that's a very important monitoring capability and also gives you performance information. But that's a clear thing where the tooling that's already there is really valuable and continuity of that tooling is worth having. But when it comes to some things like JMX or the JCommand API that's used to control the JVM, I don't know whether that will necessarily go into native image. It may be that that's an option, but it won't be in by default. Right, I think I've run out of questions there, unless there's something off the end of my screen. Okay, well, I'm about to end, so I think we've had time there. If anyone wants any more questions, I'll be happy to talk on the Hoover channel. And thank you very much for listening.